Hello and welcome to another Tycho video. Today I'm going to be talking a little bit about satellite observing. First I'll start off with a little bit of the history behind satellite observing, and I'll also go into some detail on optical versus radar measurements. And then finally, for those of you who might be interested in observing satellites, I'll also conclude with some recommendations as to what constitutes the ideal telescope for observing satellites. So with that, let's go ahead and get started. Project Moonwatch is one of the earliest citizen science projects started in 1956. It was initiated by the Smithsonian Astrophysical Observatory to enlist amateur astronomers to observe and track artificial satellites. And this was partly because professional observatories alone would not be sufficient to track satellites effectively. In other words, they needed global coverage, including locations where professional telescopes were not available. Project Moonwatch continued up until 1975, when more advanced systems specifically designed for tracking satellites had taken over. Now, what are some of these more advanced systems? One is the Baker-Nunn camera network that, to be more accurate, coexisted with Project Moonwatch from the 1950s to the 1970s. These were essentially automated photographic tracking stations that were equipped with fast, wide-field optics and precision mounts so that they could photograph satellites with exposure times matched to their orbits. They were also quite accurate, being able to pinpoint satellites to within a few arc seconds. Minitrack was another tracking network developed in the 1950s by the Naval Research Laboratory, and it could detect and track satellites without any optical observation, even during the day or during cloudy weather. This provided real-time tracking and trajectory predictions, which were crucial for space operations. However, it was a passive system, meaning that it relied on the satellites being equipped with a radio beacon emitting at a specific frequency, such as 108 MHz used by the Vanguard satellites. In the late 1950s, the Naval Space Surveillance System was developed. This operated as a continuous radar fence across the southern U.S. Its purpose was to detect all objects in low Earth orbit passing overhead, and it became operational in 1961. It was subsequently replaced in 2019 with a more modern design. Now, the Space Fence system is radar-based, and it is largely limited to low Earth orbits. When it comes to higher orbits, it is generally necessary to rely on optical tracking with telescopes. In the 1970s, the development of the ground-based electro-optical deep space surveillance telescopes began. These have a 1 meter aperture and 1 degree field of view, and were among the first to use digital imaging. A very recent development in this arena is the creatively named Space Surveillance Telescope, which has an aperture of 3.5 meters and an extremely wide field of view of 6 degrees, about 6 full moons across. It uses a large mosaic of CCDs. In essence, it is not too different from that of the LSST Vera Rubin telescope that is expected to achieve first light later this year. Now, unlike asteroids or comets, there is no concept of discovering an artificial satellite. So why would an amateur astronomer want to get involved in observing artificial satellites, especially since there is no longer a global network like Project Moonwatch? For one, it is still possible to produce useful observations related to the position and brightness of a satellite. For example, consider the ACS-3 solar sail technology demonstrator that was launched last year. It is bright enough that even with modest equipment, amateur astronomers were able to determine from its brightness over time that it was tumbling and experiencing control issues. This was later determined to be a result of a bent support arm. And secondly, it also offers a way to learn through experimentation. It is one thing to read in a book about the different orbits, but another to actually see an object move through the field of view, exhibiting a longer or shorter streak depending on how fast it is moving. Finally, most satellites are also fairly bright, so this is a part of astronomy that can be done even in light-polluted areas. So the common theme throughout the history overview is that the vast majority of imaging instruments and telescopes tend to provide a very wide field of view, and they also tend to operate at a very fast focal ratio, f2 or faster. So when I am imaging a satellite in low Earth orbit, I tend to go with a camera lens. This is the Samyang 135mm camera lens, and it operates at f2 focal ratio. And when paired with the Sony IMX571 sensor, it offers a 70 square degree field of view. Now, when I need to go deeper to reach a fainter limiting magnitude, for example, for a satellite in geo orbit, then I go for something a little bit different. This is the Celestron Raza. This is the 8-inch or 200 millimeter version. And it also, just like the camera lens, it also operates at f2 focal ratio. And when paired with the same size sensor, the Sony IMX571, it offers a 7 square degree field of view. So this is a very nice design. It is purpose built to operate at f2. So mechanically and optically, you really couldn't ask for more. The focuser is very nice. I've been using it for the past several months with no issues. So hopefully this gives you some idea of what to look for if you are in fact interested in observing satellites. So that's about it for today's video. I want to thank you for watching and see you next time.